Zivadinovic wasn't able to come here, and I was thinking that it would be good that I tell you briefly what they have done during this summer, because they are Laz Zivadinovic and Daniel Milic are students of the first and the third year of Bachelor Studies at our faculty, and they did some small research projects, and I helped them technically in some implementation of some creations to a code. We were investigating the connection between, actually, comparison between the dynamical model, the density profile of the dynamical models and body simulations of the galaxy disk of the Milky Way, and how we can connect that with stellar space densities determined by Monte Carlo method. So, sorry. When we are investigating galactic structure, we need to know what is the space distribution of some stars. If you know, for example, the space distributions of stars of different spectral types, we can see how look like the evolution in some part of the galaxy, and also we can find some metallicity gradient from the center to the edge of the galaxies. Also, when we are dealing with a large number of stars, we need to use some statistical methods, because we cannot derive the distances for a large number of stars in some solid angle. So the main goal is to solve the equation of the star statistics. This is the equation, and we want to derive star space densities, actually to distribute stars from some range of apparent magnitudes to distance intervals. So if we apply Monte Carlo method, we can do that. Of course, it is done in previous works, and to do that, we need to assume some function for the luminosity function. Of course, the natural is to assume that it is a normal distribution for the luminosity function. And if we rewrite equation 1, we can get some equation like this. This is a space density on the stars, actually. Sorry. So, of course, we need to include some effects like Malkin's bias, because we need to account stars that are not so too bright, so we cannot see them. Then what is the procedure? For every observed magnitude, for some stars, we randomly attached to it some absolute magnitude randomly taken from the Gaussian distribution. So if we do that, we will have randomly distributed stars in some volume. And after repeated of some time, we will get some mean value of the stars and the standard deviation. Actually, mean value and error of these processes. So this is a data set taken from this survey, and we didn't use all these stars. This is K giants, because they are very bright, and on some set of these stars from the field of view, we also try to see how good is normal distribution as a approximate distribution of the luminosity function, actually in the absolute magnitudes, and it is a pretty good agreement with the normal distribution. And this is correction for the Martin's bias for this data set. So what is the main idea? Actually, we wanted to see what is the stellar number density in two directions, in the galactic pole, in the direction of the galactic pole and the galactic center. And if our method of determining stellar space density is good in direction of the galactic pole, then the differences that we would have if we did it for the galactic center would arise due to extinction in the disk of the galaxy. So it could be some tracer for the gas and dust in the galactic disk. Also, what is the other part of the project? Okay, this is done for the vicinity of the sun. It's half 1 kiloparsec, and you see the blue dots are derived counts, and the red dots are true counts of decay dwarfs. And this is the stellar density. Okay, this is counts. This is stellar density, stars per cubic parsec. And the agreement is pretty good because we didn't have too much stars in this catalog. It was about 500. So we can say that the method works. The other part of the project was to build an n-body system, actually to run n-body simulation of the spiral galaxy, which consists of bulge disk and dark matter halo. And we are interested for density profiles of this disk in two directions, in the radial direction from the center and in the direction which is normal to these directions. And also try to see what are the values of these scale ends derived from the stellar space densities. Actually, we take a small part of the density profile, which we can approximate with the linear function, and to see how it can serve us to find these values of the scale ends in these two directions, radial and on the z direction. And we use galactics for the initial conditions of the galaxy and get 2 for running simulation. I will not speak a lot of this. I will speak tomorrow when I will talk about something length. And what is actually the idea? What we have done till now, we have a Monte Carlo method which works, and it works for the vicinity of the sun, and we have a model that was generated, and the density profiles of baryonic matter actually, density profiles of the stars, but most of the baryonic matter is contained within stars, so we can approximate that it is all baryonic matter in the galaxy. And we can compare that generated profile from the n-body simulations with observations and stellar space densities derived from those observations. Of course, for the small part of the distance intervals, because we are interested to, that small parts will be much smaller than the scale length in the disk. And of course, we can check that for some specific spectral class, and to see are they obeying the general profile of baryonic matter. Actually, does we have the same density profile for main second stars and red giants and so on, and from that try to conclude something about the evolution of the stars in specific parts of the galaxy disks. And of course, the end would be to make comparison between two directions, galactic pole and galactic center, and it is for the future. So this was just a briefly information about progress report, about something what they have done and what is planning to be done in the future. Thank you. Yes.
Have you looked at the Green and Finkbeiner paper where they derived the red main as a function of distance in lots of directions?
Sorry, can you repeat? I didn't hear you.
I'm sorry. Have you looked at the Green and Finkbeiner paper? They actually have a website where you can get the amount of extinction as a function of distance in different directions.
No, we didn't, but we can do that for comparison in the end when we derive some conclusion about the extinctions from this work.
I congratulate you because
Sorry.
if I heard well, first and second year students
Yes.
of
Then
the
you
bachelor
is the
studies
first year student of bachelor
work
studies.
on this
Yes.
problem. I congratulate, and I just want to
What you
ask-
said? You?
congratulate.
Thank you.
And I just want to ask in which way you model Maltese guys.
Well, we take this expression from some work that is done. I don't know. I'm not sure who is the author for this, but we just implemented in here. So this is a normal distribution for the luminosity function, and it will affect the mean value of the absolute magnitude. So we implemented here like a correction of the distribution.
Okay, thanks.
Thank you.
the foreigners, and unfortunately they could not come. So, but the talks will be conducted